All right. So chapter 6 and chapter 7 and chapter 8 really deals with probabilities. So a lot of the stuff that we're going to look at, if you've ever played any type of game with dice or cards or coins and stuff like that, it is exactly that's what we're going to be looking at. If you do not know something about cards or anything else like that, don't worry. Just ask, and I will tell you what's the number of cards in so far. Up until recently, I assumed most people got those, but that hasn't been the case in my last 3 classes. So if you are not familiar with how a deck of cards works and stuff like that, just ask, because there will be problems with decks of cards. And I'll talk about those when we get to them. All right. So first few little definitions and stuff like that we're going to talk about, and then we'll go into some of the problems with them. First thing we want to look at is what's known as a random experiment. So there is very specific criteria that makes it a random experiment. The first one is there has to be exactly one outcome for every trial. Okay. So if you remember back to your algebra classes, it's basically a function. There's one answer. All right. We can't have multiple possibilities or multiple possible outcomes for one trial. So flipping a coin, when you flip the coin, it is either going to end up being tails or heads. It cannot be tails and heads at the same time. Okay? So when you flip it, you're going to get one specific outcome. The second thing that's very important is the outcome of the experiment is unknown or uncertain. So you do not know what is going to happen every time you flip that coin. Okay? And the last thing, the set of all distinct outcomes can be specified, and it's called a sample space. So the first two are the really key things. The last one is you want to be able to list out all the possible outcomes. Okay. Any questions on those? That makes sense? The other thing is ask questions. If you're stuck on something, ask. Don't wait until 3-4 classes later and you're totally lost. All right, 2 more definitions. The first one is outcome. Outcome is any member of the sample space. So yes.
What's it called? Sample space. Thank you.
Sample space is a list of all outcomes, or a list of all possibilities. So an outcome is any member of that sample space. So an outcome for flipping a coin is heads or tails. So heads and tails is your sample space. An outcome would be heads, or an outcome would be tails. An event is a set of outcomes. So all of your outcomes is a sample space. An event would be basically like a subset of that sample space. Okay. So if we're rolling a die, my sample space is 1, 2, 3, 4, 5, 6. We're going to assume, unless I tell you otherwise, assume a die is 6 sides. Okay. For anybody who plays other games that have multiple-sided dies, we're going to assume a die has 6 sides, unless I tell you it's another sided die. So the sample space would be 1, 2, 3, 4, 5, 6. An outcome would be 2. Like it's just one of those possibilities. An event could be all the even numbers. So an event could be 2, 4, 6. So it's a subset of that sample space. All right. So let's look at a couple experiments. Tossing a coin. So what are the 3 criteria of my random experiment that we just talked about? Right. So if I toss a coin, do I have one distinct outcome? Yes. Good. If I toss a coin, do I know what it's going to come up next? No. So it passes that. And can I list the sample space for a coin? Yes. So my sample space for this would be heads, or actually head and tail. That would be my sample space. So this is a random experiment. Toss a coin 3 times and observe the number of heads. Is this a random experiment? Okay, so every time I toss 3 coins, I'm going to get a distinct outcome, correct? Okay. Do I know the outcome ahead of time? No. All right. What's the sample space for tossing a coin 3 times? No. No, but good thought. So the sample space is all of my possible outcomes. Okay. So my outcomes of this, I'm observing the number of heads, correct? So my sample space for this, I could have no heads. I could have 1 head. I could have 2 heads, or I can have 3 heads. That's my sample space for this. So we're not looking at heads or tails. We're looking at how many heads I get when I flip that coin. So in this case, my sample space is 0, 1, 2, or 3, because that's how many different heads I could possibly have when I flip that coin. Okay? Does that make sense? Okay. Because that's actually the harder one. Because like everybody, it's heads and tails. Like you have to fit your sample space to what your outcomes would be in that situation. All right. Okay. Assume we have a deck of playing cards consisting of 13 hearts, 13 clubs, 13 spades, 13 diamonds. So a deck of cards has 52 cards. There's 4 suits in them: hearts, clubs, spades, and diamonds. 2 of them are black, clubs and spades. 2 of them are red, diamonds and hearts. The cards are always from are 1 through 10, and then Jack, Queen, King, and Ace. Okay. So, is this a random experiment? Yes. If we draw a card, that's random, right? There's going to be 1 outcome. There's only going to be 1 suit on that card. Okay, so that fits that. Do we know the outcome ahead of time? No. So that's random. What is the sample space for this one?
Any of the suits.
The suits. So my sample space would be hearts, clubs, spades, or diamonds. That would be my sample space. An event could be a black suit, which in this case would be just clubs and spades. So notice how the event is a subgroup of the sample space. So inspect the transistor to determine if it meets quality control standards. It's a little electronic part. It could say inspect a case of bananas to determine if it meets quality control standards. It doesn't actually matter what they're inspecting. Does it meet the criteria for a random experiment? Is there 1 outcome for every option? Yeah, it either meets it or it doesn't, right? So those are the only two options. If it meets it, we're good. If it doesn't meet it, we're throwing it away. Okay. So it has now, do they know the outcome before they look at it? No. So it meets that. And what was the sample space that I already mentioned? Right. Meets or fails. Huh? Oh. Oh no, you're fine. You're fine. I didn't know that I heard a question. So I said,
I
well,
was just saying, like, if there's like only one option, like if there's only one result, then it's not gonna be random. You know what I mean?
correct. Yeah. So if there's only one possible outcome, then you would know it ahead of time,
Yeah.
and therefore that would not be a random experiment. Yes. There's other situations where like you can kind of predict what the outcome is going to be, and therefore it wouldn't necessarily be random. So a great example of that would be a magician when they're doing things with decks of cards. They specifically do it. It looks random. It looks like that whole concept, but they know the outcome. So that would not be a random experiment because they know what's going to come up next. Yes.
If we were to get a question like this on the homework and it wants us to put in like words, would it say like which words to use? Like instead of saying yeast, it could be cast, basically cast.
It should give you some kind of concept in the problem, I believe. So like in terms of spelling and stuff like that, that shouldn't be an issue. I think it gives you options, actually, most of them. Yeah, no, it shouldn't. I haven't looked, in all honesty, but knowing the way they set up most of these programs, they have to do something to make sure that it's not like because they don't want to have to put a ton of options in there to solve it. So they probably give you like a multiple choice, like what's the sample space type thing. So no problem. All right. Oh, wrong screen. There we go. All right. We have two different ways, and I hate the way Hawks calls this. There's two different ways to look at probabilities. Okay. There's theoretical and there's experimental. They call it relative frequency and the classical approach, and I don't know why. Because nobody else does this. This is known as experimental. And I think I spelled it correctly. Okay, so experimental means we're actually doing the trials to determine what's going to happen. All right. So to figure out the probability of that, all we're going to do is we're going to divide what we wanted. What is that? The event that I'm looking at, and divide it by how many times I did the actual experiment. Okay. So for example, let's see if I can find my thing. Coins. I want a coin flipper. There we go. All right, so we're gonna flip 200 coins. And it doesn't actually give me the. Great, how nice. Not going to help me. I need the count.
You can do like random number.
That's what I just did, random.org, and it didn't actually count up how many there was.
Well, I mean, like on Google, you can put like random number generator and go between 1 and 2.
Oh, that's I need the count. That's the problem. I want the actual count. Okay, never mind. I'll just make flips up. All right, let's say we flipped a coin 100 times. And it came out, there was 48 heads. Okay, so I flipped the coin 100 times, and we had 48 heads. What is the probability that I got heads?
Theoretically, 50%.
No. I got 48 heads out of 100 flips. 48 out of 100, so I would do 48 divided by 100. So the chances of me getting heads was 48%. Okay. You said one very important word before you gave me the answer.
Theoretically.
Correct. What are we talking about right now? Right. There's a big difference. That's the difference between those two. So in an experimental situation, we're doing it. It does not always have to come out to be exactly what you'd expect it to do. However, the more we do of them, the closer it should get to that actual value. So in this situation, like here, actually, let's see if I can zoom this in a little bit. It's a little bigger. So if we look here, this is the number of flips and how many heads came out if we flipped it up to 42 times. So as you can see, it starts bouncing back and forth, and then it's starting to level off. That theoretical 50%, because there's only two options, is right there. Notice that right now it's below that. And this is the relative frequency. Now, if we started doing for 200 to 300 flips, you can start seeing that it is getting very close to that line of 50%. And if we did it over 1,000 times, it is pretty much at that line. So the more and more that we do, the closer and closer it should get to that theoretical value. However, it might never actually get to that exact value. Okay? So that's the concept of experimenting, is that you might not get exactly what you would expect in a theoretical situation. However, there's some situations that you really can't do a theoretical model for. Okay, like if I want to look at the number of accidents of red cars on the highway, okay, I'm not going to be able to come up with a theoretical number for that. To do that, I'd actually look at accident reports and determine how many red cars were in accidents and come up with that probability. So that would be an experimental probability that I could not come up with a theoretical one. When we're talking about games and stuff like that, most of them, yes, you can absolutely come up with a theoretical probability for it. They call theoretical the classical probability. It's theoretical. And a theoretical probability, we are looking at the sample space. And we're looking at that event that I'm picking. So if we're thinking about heads, there's one head out of two possible outcomes in the sample space. So the theoretical probability of getting heads is 50%. Okay? That would be theoretical. What's the probability of getting evens on a normal die?
50%.
Right, because it's 2, 4, and 6. So there's 3 options out of 6 possible outcomes. So 3 divided by 6 is 50%. What's the probability of getting a club out of a deck of cards? 13. 13 out of 52, which would be what? It'd be 1 out of 4. How many suits? 4 suits, and I only wanted 1. Okay, so it's 1/4. 13 over 52 also gives you 1/4 if you reduce it. That goes back to looking at what my sample space was. Since I was talking about suits, we don't need to look at every possible card. We just need to look at the 4 suits. So my sample space was 4, and I really only wanted clubs. Okay, that goes back to that concept of looking at what's that options there. So what is the problem? Yes.
The experimental ingredient, do they ever like have like, does the other one they put like what? Or do they describe what K and N means in their terms, or do they not list that? Just for like the thing.
So K is, hold on. K is the number of times the event happened, and N is the number of times that you've done the experiment. It actually should be very similar to this. A is the top number is the number of ones you want, whatever you wanted, that's the event. And the bottom is the number in the sample space in this situation, because that's the total of options that you have. So we're going to go back to that flipping a coin 3 times. What is the probability of getting 2 or more heads? So, first thing, yes. So, first thing I need to know is how many different ways I can get 2 heads, right? So, when we're looking at coming up with our options for this, we need to write out all the different ways that I can get options I can get when I'm flipping 3 coins. Okay? So, I could get heads or tails on my first coin, right? Correct? My second coin, I could also get heads or tails, right? Heads or tails. And on my third coin, I could also get heads or tails, right? So I have heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, 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 heads, and tails, tails, tails. So I have 8 options out of those 3 coins, correct? So that right there would be my sample space of all the different ways that I would get with flipping 3 coins. How many of them have 2 heads? So that one, that one, that one, that one. So 4 of them, or 1/2. Okay. So when you're looking at a theoretical probability, you need to list out all the possible ways that you could flip those 3 coins, or all the possible ways that could happen, and then look for your event after that. With this, in this case, it's 4. So there's 4 possibilities. So again, it's 50, ends up being 50% of me getting 2 heads. What's the probability of me getting 3 heads? One out of 8. There's only one option that gives me 3 heads. What's the probability of me getting no heads? One out of 8. Okay. So sometimes you have to, again, this goes back to that English thing. It's like how they're wording it. No heads means what? 3 tails. Okay. Because you only have 2 options. If it's not a head, it's a tail. So you have to think about those things as well. All right. So gamblers made a weighted die. So he rolled it 33 times. So if it's a standard die, a normal die, if we did theoretically, every option should come out 1/6 of the times, right? Yeah, but this is a weighted die. So I want you to find me the relative frequency or the experimental probability of each of the numbers. So what's the probability of getting a 1? What's the probability of getting a 2, a 3, a 4, a 5, and a 6? And when you're dividing them, you're going to divide them all by 33. Because we had 33 attempts. The 7 twos? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Oh, yep, right, the 7. What I was going to do at the end is I was going to add them all, make sure it adds 30 to 32 or 33. And then figure out where I screwed up. $21, $26, $31, $33. I think I got them all. Bad gambler. You wouldn't want your weighted die to be that obvious. Leaving them as a fraction is just as good as changing it to a decimal. So unless the problem specifically asks you to give it as a percent or a decimal rounded to a certain number of digits, a fraction is just as good of an answer. Okay. So if all the outcomes have an equal payoff, which number should the gambler bet on? Obviously, it should bet on 1 in this case. And if he uses that die too many times at the table, it's probably not walking out alive. Is this an experimental or theoretical? This is experimental. Theoretical, even on a weighted die, would be 1 out of 6. Because it's weighted, it skews way off of what the theoretical would be. Okay. And that's how you test things a lot of times. So here's an interesting, in football, what do they do at the very beginning of every football game? They flip a coin to determine who goes first, right? Who gets to choose the ball. Normally, you only ever see them actually do this at the Super Bowl, but they do it in every game. And then they do it in overtime. So a statistician actually went through and looked because they've been doing this since the 1960s. So there's a ton of data of them flipping a coin. What he found was when you flip a coin, whatever's on top when you flip the coin actually has a slightly increased percentage of coming out that one. So if tails is on top, tails has a better opportunity of coming out than heads. It's slight, but he actually found that it varies based on that. So it's something to do with the weighting. It's not huge, but it's definitely a little bit. Yeah.
How slight? Like, are we talking like half a percentage?
Oh yeah, it was very small. It wasn't like a huge amount. Let's see if I can. So they did the study. It said coins flipped in the air and caught in the hand had a 50.8% chance of landing on the same side they started from. And they did the study. They used 350,757 flips that they looked at. So that's a lot of, like, when you get that high, you'd expect it to be pretty close to 50-50, a 50% chance. So 50.8 is a significant difference in that. So,
I
yeah.
mean, it's almost a full percentage.
Yeah, so that's quite a bit of a difference there. So, all right. Let's look at some laws of probability. So, probability of 0 means it can never, ever happen. Not, oh, it might never happen. It will never happen. Okay? So, for example, flipping a coin, you are never going to get lizard. Okay? Because it's always going to be heads or tails. That's the probability of 0. Right? The converse of that, a probability of 1, means the event will always happen. So if I roll a die, I'm going to get a number from 1 to 6. Okay. Next, all probabilities between 0 and 1 inclusively. So you are never going to have a probability that is less than 0. You will never have a probability that is greater than 1. Okay, so it'll always be a decimal between 0 and 1, including 0 and 1. So when you do your calculations, if you screwed up and you got a number bigger than 1, you know you screwed up. Chances of you getting a negative number are slim unless you really screwed up. But you'll always have a number between 0 and 1. The sum of all probabilities has to equal 1. So if I take the probability of getting a head, the probability of getting a tail, add them up, I'm going to get 1. And that last experiment that we did with the weighted die, if I added up all those probabilities, I'd have gotten 33 over 33, which was 1. Okay. Yes. Oh, if it occurred, a probability of 1 will always occur. It is guaranteed to happen. Which is rare. Like, it's not something that normally, like, that's not something that's going to happen very often in most places. Same thing like a 0 is not going to happen. Most things in life, there's always either a slim chance of it happening or a slim chance of it not happening. So. Compound events are when we're looking at 2 or more events. So if we're looking at somebody that has an annual income greater than 50,000 and subscribes to 1 or more sports magazines, I guess now we could say more than 1 sports website or more than 1 streaming service. Okay, so when we're looking at 2 different options or 2 different things, and we're looking at how they interact, those are compound events. Okay, so at the bottom, anybody know what that's called? That is a Venn diagram. So you're going to see those. Those come up quite often when we're looking at probability. And so we have the event A and event B, and there was a little overlap in between those two. That overlap is known as a union. So the union of them is the overlap between A and B. And it's denoted by that little U symbol. So the union is in between those. Another way, depending on how you've heard it before, you could say that is and. So it's A and B when it happens. So that's where both events happened. Actually, I lied. That's intersection. I had it completely backwards. Yes.
I was gonna ask, so, well, I mean, I guess this is the intersection.
I did intersection, yes.
Yeah, would it be with, so could two or more have a union together?
So I just explained the intersection completely. Intersection is only the space in between. And intersection is the N symbol. So it's A intersecting B, which is also A and B. They both have to happen. Union is everything. So union's all of A and all of B, including the middle. So A union B or A or B. Or both. We can also have what's known as the complement to the event. Complement is not necessarily a good thing in math. Complementing is not that event, so it's the opposite of it. So what is the complement of heads in a coin? Tails. What is the complement of 1 on a die? Almost. Yeah, it's all of them. So it's the exact opposite. So if I say 1 on a die, the complement of it is everything other than the 1. 2, 3, 4, 5, 6. Okay. So yeah, it's the complement is the exact opposite of it. That actually is helpful because if I wanted to find what's the probability of getting a bunch of different options there, sometimes it's easier to look at the opposite of it and then subtract from 1 to find that answer. Okay. Then finding doing all the extra work to find that other options, it's easier to find the simple one first. So the complement actually comes in handy when we're doing some larger calculations. All right. Has anybody in here never been to the casino? Okay. Has everybody in here seen a roulette table at some point? Okay. So a roulette table has numbers 1 through 36. They're black and red. And then there's 2 green spaces on it, 0 and 00. Those are the house numbers. So when you're looking at a roulette table for betting, you can bet black or red. It's one of the options you can bet. You can bet anything else, but black and red. If you bet black, you'll double the money you bet. You bet red, you can double if it lands on it. However, the probability that you land on them isn't exactly 50-50 because of those 2 green ones. That's how the house makes their money. Because if it was exact, then the house would make no money. Because over time, it would balance out to be exact. The money they paid out would be exactly the money they got in. So, what is the probability of the roulette ball landing in a red pocket? So, how many red numbers are on a roulette table? There's 36 total numbers between black and red. So it would be half those, right? Which would be what? 18. 18 is half of 36. So there's 18 red. Okay, so 18. And how many numbers are on the roulette table? There's 38. 36 red, black, plus the 0 and plus the double 0. So there's 38. So the probability of me landing a roulette ball in a red pocket is 18 out of 38. Okay, does that make sense? Okay. What is the probability of a roulette ball not landing in a red pocket? That's the complement of it, right? That is the exact opposite of landing in red. So not red. The bottom is still 38. The top would be the opposite of it. So how many numbers are left? There's 20 numbers left. Because in essence, I have to do 1 minus 18 over 38. This is where those extra 2 come in that always screws everybody up. Because you would think, oh, okay, it's half red, half black. It's going to be the exact same. But it's not because of those 2 green ones. Green ones always screw everything up. I believe, if I remember right. Is the European tables are different. Oh, it's the French table that's different. So a French table only has 1 0. So yeah, so a French table is actually better for you than an American table. All right. Let's look at odds. So odds are slightly different. All right. So probability is what you want over the total number of options, basically. And that's probability. Odds are what you want over what you don't want. Okay. So your odds in favor are what you want over what you don't want. Your odds against are what you don't want over what you want. So if I want the odds of red, what I want, there's 18 red on the on the table. That's the probability of red. What's the probability of not red? How many not reds were there? 20. So that is the odds of getting red, is 18 out of 20. So that's how you can get odds that are like 2-to-1 and 3-to-1, those type of things. Yes.
What would be like the benefit of using odds and like probability? Is it just like preference?
It's gambling. Gambling typically uses odds instead of probability. There is no real benefit to it. So it's just another way to look at it. And unfortunately, it's one of those ones that you see quite often because you hear like odds all the time. So I need to actually make sure you understand what that means. Yes.
Would stocks use probability or odds?
Stocks uses neither.
Okay.
So here's the no, actually, that's a very good question. So why would stocks not everything I've talked about today, why do stocks not fit into it?
Well, because it's affected by more than just random chance.
Right. So it is not a random experiment. Therefore, this doesn't work. Okay. The very first thing we talked about was a random experiment. So everything we've done after that point needs to fit the criteria of a random experiment. If it doesn't, then it is not. You can't do this type of probability and stuff with it. So when you're looking at like odds for sporting events and stuff like that, those are not a random experiment. There's other stuff that goes into it. That's where your odds makers are making up those numbers. It is not calculated. And a lot of times it's based on who's betting. So when you go to a casino and bet on a game, the odds they give you initially is what they predict is going to happen. After people are betting, they will change those odds to fit the theme that's going. So if everybody's, for example, so Aaron Judge is probably going to win the MVP in the American League because so people were betting that he's going to win it. As more and more people bet it and more data came up, the odds of him winning it went up so that the amount of money you would earn would go down from those bets. So that's where, like in those type of situations, the odds are not true odds. They're using it.
Well, I mean, I guess this is more of a philosophical question, I guess, but wouldn't on some level everything be a probability?
Okay, so now I will talk about the third type that I didn't actually talk about on purpose. So we talked about experiments, we talked about theoretical, right? There's a third one that I don't particularly like because it's not mathematical. It's called subjective. That's where those situations come into play. There is no actual data that you can sit there and go, oh, yeah, this is always going to happen. It's more subjective. So what do you believe is going to happen? What do you think is going to happen? And you can say, oh, there's a 50% probability that this is going to happen, or there's a 75% chance that this is going to happen. We hear it all the time in weather. Weather's a great example of this. It is subjective. Okay. So they're saying there's a 60% chance it's going to rain today. That's subjective. Yes, they're basing it on some data, but in the end, they're choosing that number. There is no mathematical equation that is giving them that number. Okay, that's all subjective. Same thing with sports and odds, same thing with your stocks and things like that. Those are very subjective things. You're trying to predict what's happening down the line, so it's very subjective in that respect. Okay, and there's lots of things that can come up to change what ends up happening. A great example is what happened to GameStop. That was a perfect example. Like GameStop didn't automatically start making money. People put it out there that, oh, let's boost the stock up there. Like, so people started buying it, which increased the stock price. It was like nothing. The company did nothing to do that. It was literally the internet that did it. And the people that made money were the ones who started the rumor, because they bought early, pumped up the stock online. So people kept buying it higher and higher. And when they said enough, they sold at the height. And then the stock dropped again. And the people who held on too long lost money. So that's where your subjective options comes into play. Once you get human, the philosophy and all that other stuff into play, then it's no longer truly mathematical. What are the odds against of getting a green. So what are the odds against of getting a green? So how many are not green? 36. How many are green? 2. So the odds against of getting green are 36 over 2, or 18 to 1. Yes.
You wouldn't have to just write that as a whole number.
Yeah. No, you'd write it as 18 to 1 or 18 over 1. Because you need the other piece of information to make it an odd. You wouldn't just say the odds are 18. You need it 18 to something. It's like a ratio, you always have that extra piece.
You were saying, you just write it.
Yeah.
Will be write it as a ratio instead of a fraction.
You could. Like I said, actually, I actually even said 18 to 1. Yeah, you could write it as 18 over 1, 18 colon 1, 18 to 1. They're all the same thing. It just depends on who's talking and what you're at, the context you're using it in. When you're looking at it in terms of betting, they'll say 18 to 1. So that's typically where you're looking at it as. So, all right. A few more terms. So we have 2 different ways that you can look at events. In the other graph we looked at, the 2 circles were overlapping. That means there was some interaction between the 2. And then these 2 are completely separate. These are known as mutually exclusive. So mutually exclusive events have no impact on each other. They're completely and utterly separate in the respects. That means the intersection of, or the union of them, is just the sum of the 2 probabilities. So probability of A, probability of B. And there is no intersection. Intersection would be 0. So the probability of getting a red ball or a red number on roulette and the probability of getting a black number on a roulette, those are mutually exclusive events. There is no number that is both black and red. Okay, so those are mutually exclusive events. So we can add those 2 probabilities together to get the probability of getting either black or red.
This would also be like a random. Where it's just like you get one answer or you get the other answer.
No, so each of these is their own experiment. So like flipping a coin and rolling a die. So A could be flipping a coin, B could be rolling a die. Okay, there is no interaction between those 2. If I chose a card out of a deck of cards, and then I chose another card out of the deck of cards, there is some interaction between those 2. So those would not be mutually exclusive. Because by pulling the first card out, I've changed the odds. So those wouldn't necessarily be mutually exclusive. If I put the card back and did it again, they would be, because the odds and stuff would stay the same. So mutually exclusive does not necessarily have to be the same type of thing. It can be 2 completely different events. There's just no interaction between them. Most situations are not that way. Most situations, there is some interaction between them. So in that situation, if I wanted to find the union of the probability, if I just added the probability of A and the probability of B together, I would in essence be counting this section in here twice. Okay, so if probability of A was 40% or 0.4, and the probability of B was 0.7. If I added those together, I'd get 1.1, right? Okay, because that part right there is part of A and part of B. So if I told you that part right there was 30%, the intersection of A and B, I would want to subtract that off. So I'd get 0.80. So that means now if I added up the A and the B, it'd be 0.80 because that would include both of them. But it wouldn't count that middle part twice. Does that make sense? That's the difference between mutually exclusive and generally. Because mutually exclusive, there's no overlap. So if I could just add them, because the overlap is 0. In this situation, since they overlap, if I just added them, I'm going to add that piece in the middle twice. And I don't want to add that piece in the middle twice. So I have to subtract out one of it. Okay. 0.8 would be the probability of A intersection or union B. Let's do this one. I'm just getting the questions up in a second. All right. So there's 1,000 policies here. Okay. It actually tells it up there, so it's not secret information. What is the probability that the husband will have between $50,000 and $100,000 of insurance? Yeah. So there's over 1,000, right? Oh, sorry. So my bottom number is going to be 1,000. And so how many policies did the husband have between 50 and 100,000? That's this one, right? That's all the ones for a husband between 50 and 100,000. So I have to add all those together. So 270. So it'd be 27%. Okay. What's the probability that the wife will have between 100,000 and 150,000? So we're going to add 100 to 150,000, right? So that's the 20, the 10, the 25, and the 25. Wife, so it's those. So in this case, it'd be 80 over 1,000 or 8%. What's the probability that the wife will have more than 150,000 or the husband will have more than 150,000? So what's the probability the wife will have more than 150,000 or the husband will have more than 150,000? So we have two events, correct? Okay. So let's do them. Let's look at it. So the probability of wife greater than 150 is what? 60 over 1,000. What's the probability of the husband over 150? 120. And they want or, right? So we'll say that's A and that's B. So they want the union of A and B. What'd you get? So we have to ask ourselves a question before we do this. Are these two events mutually exclusive? Okay. Where's the overlap? We have an overlap right here. We counted that number twice, correct? Okay. So I have to add these two and subtract off that 15. So I get 180 minus the 15, which is 165 over 1,000. Okay. Because they're not mutually exclusive, I have to subtract that extra piece off. Okay. Otherwise, we counted it twice. So we had two events, not mutually exclusive. Find the probability of each one, add them, and subtract off the overlap. What's the probability that the wife will not have between $0 and $50,000 of insurance?
All of them should be the-
We could do that. So one option is yes, add up everything except for the top row for the women, right? What's the other way we could do it? What's the complement of it? We could just add up the first row, right? And subtract it. So what's the first row? 700. That was a lot easier than adding up all the other numbers, right? So the opposite of that, or the complement to that, would be 1,000 minus 700, which is right. So the answer would be 300 over 1,000. That's where that complement comes into play. Sometimes it's easier to do the opposite of it than to do what they're asking, because it's more numbers you have to add up. Okay? So that's where that complement can come in and help you. What's the probability that the husband will have more than $50,000 of insurance? What was it? Yeah. I had to do the quick math in my head. Yes, 510 over 1,000. So you can start to see how we use those probabilities. All right, we're done for today.